Hello everybody, this is the notes for Calculus, section 3 of chapter 2. We are talking about a couple of different types of functions, polynomial functions and rational functions. Okay, there are certain properties that happen that we need to know about in order to make sense of what the calculus is going to tell us as we get going into the calculus. So that's what this video is about. You're probably going to want to hit pause at a couple of moments to take the notes and then hear the explanation of some things. But here we go. Okay, polynomials basically is your normal looking functions. This right here looks super complicated. The idea of a polynomial is x to the third plus 7x squared minus 4x plus 2. It starts with integer powers for the exponents, integer exponents. You start with the highest power exponent and you work your way down, so cubed, squared. The first power, you work your way down to a constant. That's what it is. Those are polynomials. So the highest power of the variable, we call it the degree of the polynomial. This a sub n is right here. It's called the leading coefficient. It's the number of those highest powered x's you have. So in that example, there was one x cubed. It's a degree 3, and there's only one of those x cubed. So the leading coefficient would be 1. All right, there's a couple of properties that we need to talk about. Again, it's helping us make sense of what the calculus is going to tell us. So it's just, these are characteristics of a function. And we can get all this information just by looking at our equation and picking out pieces of information. So the first property, polynomial of degree n can have at most, doesn't have to have that many, but it can have up to n minus 1 turning points. So n is the degree. So if I had a degree 3, so something like an x cubed type function, like I wrote in that upper right corner, it can have, it's a degree 3, so it can have at most 2 turning points. Now a turning point is basically, when we talk about turning points, the graphs always go left to right, just like you read words on a page. A turning point is changing direction, going from increasing to decreasing or decreasing to increasing. Those are your turning points. So a degree 3 can have at most 2 turning points. That would be the idea of this. This is a turning point there, that is a turning point there. It doesn't have to have 2 turning points. If we just graphed x cubed, oops, x cubed looks like this. That's not a turning point at the origin there. It doesn't change direction going from increasing to decreasing. So like I said, it doesn't have to have n minus 1 turning points. It can. Degree 4 could look something like this. Degree 4 could have 3 turning points, 2, 3 turning points. All right. Second property, polynomial with even degree. Both ends are going up or both ends are going down. So basically, the ends are going in the same direction. So bottom graph here, that degree 4 I just graphed looks something like this. These are the ends that I'm talking about. If it is an even degree, the ends are going in the same direction. Now, they could both be going up like this. They could both be going down like that. Either way, it doesn't matter. Even degree, the ends are going in the same direction, either up or down. If it's an odd degree, the ends are going in opposite directions. So like that x cubed I drew earlier. This left end over here is going down, the right end is going up. It could be the other way around as well, where a degree 3 could do something like this, where the left end is going up and the right end is going down. If it's an odd degree, the ends go in opposite directions. All right, third property is telling us about which end is going in which direction. So we really focus in on the right end of the graph as x goes out towards the positive values. Okay, that's what we're talking about, end on the right side. So if the graph goes up as x becomes large, meaning the x values are going towards the positive infinity, the leading coefficient must be positive. Okay. So that's what we're looking for. If in the equation, our function, that polynomial function, if that leading coefficient is positive, the right end is going to go up. If the leading coefficient is negative, like this, that right end is going to be going down. Now, knowing what the right end does, and then combining that information with the degree, we can tell us what the left end is going to do. Okay? So the leading coefficient tells us about the right end. The degree is going to tell us what the ends are doing compared to each other. All right, that was basically it for the for the polynomial functions. Those three properties. Rational functions look like this. Basically, rational means fraction. So when we have a fraction for a function, something like 3x minus 2 over 4x plus 7. Okay, that's a rational function. The numerator is a polynomial, the denominator is a polynomial. All right, the denominator can never be 0, just like any other fraction. Okay, what I'm describing here, when you hit pause, get this stuff down in your notes. When we deal with rational functions, these things have, or let me rephrase that, rational functions can, not all of them do, but most of them do. They can have these things called asymptotes. It's what the graph is doing near either a certain x value or what the y values start to approach. So the first one is talking about a vertical asymptote. Okay? When we use the word function, what that means is we're really talking about the y value. So it says if a function gets larger in magnitude, so basically the y values are going towards either positive or negative infinity. Basically those y values are going up or they're going down without bound. So they just keep on going up or they keep on going down, the y values. If a function gets larger in magnitude without bound, so if the y values are going up or down, as x approaches a number, so as the x values get really close to 2, the y values are going to go up or the y values are going to be going down. Then at that vertical line of x equals, I just made up 2, we have a thing called a vertical asymptote. So if you look at this graph, let's look right here, put it in blue. If we look at this x value of negative 3, as these x values go towards negative 3, talking about the y values now, as the x values go towards negative 3, these y values keep going down, going towards negative infinity. From the other side, as the x values get closer to negative 3, from the positive going towards negative 3, these y values are going up. What we have there is a vertical asymptote. Now, it's not really part of the graph, but it's like a boundary helping shape the graph. So this green dashed line I'm putting there, that's our vertical asymptote. It is at x equals negative 3. We also have one, it's at x equals 0, but that's really the y-axis. If you look right here, okay? As the x values get close to 0, those y values are going up. As x gets close to 0 from the other side, those y values are going down. That's a vertical asymptote. All right. The next one. If the values of y approach a number, so as the y values get closer to a number, or let me rephrase that. If the y values approach a number, as the x values get large. So now we're talking about the ends of the graph. As x goes out towards positive infinity, or as x goes towards negative infinity. If the y values get closer to a number, we have a horizontal asymptote. And so we have one in this graph as well. A horizontal asymptote is really right here at the x-axis, which is y equals 0. Okay? As these x values get really large, our function is getting closer and closer to a y value of 0. Same thing on the other end. As these x values go towards negative infinity, those y values are getting closer to 0. So we're talking about the ends of the graph. All right, here's how you identify. Looking at this rational function, looking at the actual equation, this screen is going to tell you what to look for to say this rational function has a vertical asymptote, it has a horizontal asymptote, and what they are. All right, These asymptotes, again, they happen with rational functions only. So, the first one, to find a vertical asymptote, you are looking for the zeros of the denominator and only of the denominator. So in that example that I wrote here, let me see if I can copy this. Copy. And I don't know if I can paste it. Of course not. All right, what was the denominator there? 4x plus 7, 3 times 2, 4x plus 7. Okay. All right, so for this example, zeros of the denominator only is what you're looking for vertical asymptotes. So I just set the denominator equal to 0 and solve. That's going to be the vertical asymptote. Okay, that value of x does not make the numerator equal to 0, only the denominator. So there's a vertical asymptote, and we would write capital V, capital A for short, vertical asymptote. All right, for a horizontal asymptote, there's two situations you got to look for. If, and what we're looking at is really the degrees of the numerator and denominator. So if it's a larger degree in the denominator, so if you have something like an x over an x squared, so let's say I just threw on that x squared in that denominator of that example, that's all you need to look at. Say, hey, I got a larger degree in the larger degree in the denominator. Y equals 0 is that horizontal asymptote. The other possibility to get a horizontal asymptote, if we have the same degree top and bottom. So that example that we've used, they're the same degree. It's a degree 1 in the numerator, degree 1 in the denominator. When that happens, you look at your leading coefficients. That's 3 and 4. So this example would have a horizontal asymptote at 3/4. When it's the same degree top and bottom, leading coefficient. Hey, they're sour. All right. There's another type of asymptote we don't deal with very often, but it's called an oblique asymptote. It's not horizontal and it's not vertical. It only happens in one scenario, when the degree is 1 larger in the numerator. When that happens, you actually have to do the long division. The answer to that long division is the oblique asymptote. But like I said, we don't use that very often, so I'm just going to skip over it. Okay, so looking at this example, vertical asymptote. We're looking for the zeros of the denominator only. Oh, sours. All right, so I'm setting the denominator equal to 0. I want to know what x values make that happen. So I'm going to factor this. I like x plus 2, x plus 3, x equals -2, x equals -3. All right, now, vertical asymptotes, zeros of the denominator only. You have to look at your numerator. Do either of those x values make the numerator equal to 0? And they don't. So this one has 2 vertical asymptotes. Not a big deal, it happens. All right, horizontal asymptotes. When I look at this, we have the same degree top and bottom. When that happens, you look at your leading coefficients. So the leading coefficient of the numerator is 4, the leading coefficient of the denominator is 1, y equals 4 over 1. There's your horizontal asymptote. The oblique asymptote only happens when you have a degree 1 larger in the numerator. We don't have that. So there's no oblique asymptote. And that's it. Don't worry about that slide. All done. Take care, everybody.